everyone. Today, we are going to discuss a topic closely related to workers in the chemical industry. 2.2 Prevention of occupational disease hazards in the chemical industry. During chemical production, there are various potential hazards that may cause varying degrees of harm to employees' health. To give everyone a more intuitive understanding, let's first look at a case study. Xiao Li is a field operator at a polycarbonate plant. During his daily inspections, he comes into contact with chemicals such as naphthalene, bisphenol A, and sodium hydroxide. In some areas of the production building, noise levels exceed 85 decibels, and there are high temperatures and significant dust levels. So what occupational disease hazards are involved in these situations? What are the potential dangers? And how can they be prevented? With these questions in mind, let's study further. First, occupational disease hazard factors. These are factors or conditions generated or present in occupational activities that may adversely affect the health, safety, and work capacity of the workforce. Remember this concept as it is a foundation for our subsequent studies. Classification of occupational disease hazard factors according to sources. They are divided into harmful factors in the production process, harmful factors in the labor process, and harmful factors in the production environment. Harmful factors in the production process include chemical, physical, and biological factors. Chemical factors include toxic gases such as phosgene and carbon monoxide, as well as chemicals like bisphenol A, as in the case study. Physical factors include noise and high temperatures. Biological factors include organisms such as Bacillus anthracis. Harmful factors in the labor process include excessive work intensity and prolonged poor posture. Although this aspect is not clearly reflected in Xiao Li's work, it is important for everyone to understand this concept. Harmful factors in the production environment include unreasonable plant layout and environmental pollution. In the case study, poor factory ventilation could exacerbate the impact of these harmful factors. According to the Occupational Disease Hazard Factor Classification Catalog, they are divided into 6 categories: dust, chemical factors, physical factors, radiation factors, biological factors, and other factors. This is the standardized classification set by the state, which facilitates systematic understanding and management of these hazards. Next, let's analyze which occupational disease hazard factors are present in the case study. They mainly include dust, noise, high temperatures, and industrial toxins. Second, common occupational disease hazard factors in the chemical industry and their prevention. Please watch the 2nd of August. Kunsha, Zhongrong, major aluminum dust explosion accident detail.
The explosion dust in this accident was aluminum powder. According to the list of hazardous chemicals, the hazard code for aluminum powder is 43013, which belongs to wet-sensitive flammable materials. It will undergo a chemical reaction when exposed to a small amount of water or moisture, releasing hydrogen and heat. If the accumulated heat is not dissipated, it is prone to cause combustion, explosion, and secondary explosions. The accident workshop was located in the southwest corner of the plant area and began construction in June 2004. According to the Code for Fire Protection Design of Buildings, the fire hazard category of the accident workshop should be defined as Class B, but it was actually defined as Class E. The accident workshop had a two-story reinforced concrete frame structure, with brick walls on all four sides, and a roof made of steel beams and color steel plates. The building area was 2,145 square meters. The plan was 44.24 meters long from north to south, 24.24 meters wide from east to west, and each floor was 4.5 meters high. The accident workshop was an automobile wheel polishing workshop with 2 floors. There were 13 production lines on the first floor and 16 on the second floor, totaling 29 production lines. Each production line had 12 workstations, with a total of 348 workstations. At the time of the accident, there were 265 personnel. Grinding and polishing in the workshop were all manual operations, using handheld electric grinders, and the operation process generated a large amount of aluminum powder. The dust removal system installed in the accident workshop was completed in March 2006. Dust entered the dust removal pipeline through the suction hood above each workstation. A set of dust removal systems was shared by 48 workstations on 4 production lines. Through mechanical vibration, the belt filter separated the dust. The gas was exhausted, and the dust fell into the dust collector. A total of 8 sets of dust removal systems were installed on the first and second floors. After the renovation in 2012, the exhaust pipes of the 8 sets of dust removal systems were all connected and discharged through a main pipe. Course of the accident: at 7 on August 2, 2014, employees of the accident workshop went to work. At 7:10, the dust removal fan was turned on, and employees began operations. At 7:34, the number 1 dust collector exploded. The explosion shock wave propagated to the workshop along the dust removal pipeline, raising aluminum dust accumulated in the dust removal system and the workshop, causing an explosion. It then propagated to the second floor along the 2 north-south staircases in the workshop, resulting in a series of explosions. The accident caused 47 deaths on the spot, 28 deaths after ineffective rescue in the hospital on the same day, and 185 injuries. The accident workshop and production equipment in the workshop were destroyed, according to the 30-day reporting period stipulated in the regulations on the reporting, investigation, and handling of production safety accidents. A total of 97 people died, 163 were injured, and the direct economic loss was 351 million yuan. The casualties and economic losses were heavy, with a huge social impact. The dust removal system in the accident workshop was not cleaned as required for a long time, leading to the accumulation of aluminum dust. After the dust removal system fan was turned on, high-temperature particles generated during the grinding process formed a dust cloud above the dust collection bucket. The dust collection bucket of the number 1 dust collector was rusted and damaged, and the aluminum powder in the bucket was exposed to moisture, causing an exothermic oxidation reaction. When the ignition temperature of the dust cloud was reached, it triggered a series of explosions in the dust removal system and the workshop. Due to the absence of an explosion venting device, the high-temperature gas and combustion products generated by the explosion were instantly ejected from each suction port through the dust removal pipeline, causing all operators at workstations in the workshop to be directly impacted by the explosion, resulting in mass casualties.
Analyze the causes of the dust explosion and consider how to prevent and avoid such explosion accidents. 1. Dust source such as the mechanical crashing of solid materials and the mixing and sieving of powdered materials. In the polycarbonate factory where Jiaoli works, the dust in the finished product storage area and raw material area may be generated during material handling and storage. Hazard. Toxic dust can lead to poisoning or even death. Non-toxic dust can cause pneumoconiosis or silicosis and affect the air environment, and more seriously, it may trigger dust explosions such as the catastrophic aluminum dust explosion accident at Kunshan, Zhongrong on August 2nd. Preventive measures. Technically, start with production process design. By employing measures such as enclosed pneumatic conveying systems, individuals should protect themselves by wearing dust masks, and health monitoring should be conducted with regular medical examinations. Analyze the causes of the catastrophic aluminum dust explosion accident at Kunshan, Zhongrong on August 2nd. The direct cause was that the dust removal system in the accident workshop was not cleaned as required for an extended period, leading to the accumulation of aluminum dust. After the dust removal system's fan was activated, high temperature particles generated during the grinding process formed the dust cloud above the dust collection bucket. The dust collection bucket of dust collector number 1 became corroded and damaged. The aluminum dust inside absorbed moisture, triggering an exothermic oxidation reaction that reached the ignition temperature of the dust cloud, which then initiated a series of explosions in the dust removal system and the workshop due to the absence of explosion denting devices. The high-temperature gases and combustion products produced by the explosion were instantly expelled through the dust collection ducts and each suction port, causing all operators at the workstations to be directly subjected to the explosive shock, resulting in mass casualties. Preventive measures. Number 1. Reform processes and innovate equipment. Design the plant and production layout reasonably. Improve the design, manufacturing, installation, and modification of the dust removal system. Ensure system sealing and prevent dust leakage. Number 2. Standardize workshop. Safety production management. Number 3. Strictly implement safety protective measures. Number 2. Industrial noise. This refers to the noise produced by mechanical equipment during operation. At 60 to 70 decibels, it is noticeably loud. Exceeding 100 decibels can cause temporary hearing loss within minutes. Sources: aerodynamic noise, mechanical noise, and electromagnetic noise. The noise exceeding 85 decibels in Jiaoli's inspection area is mechanical noise generated by operating equipment. Hazards: it damages the auditory system, and long-term exposure can also affect extra-auditory systems, such as the nervous system and cardiovascular system. Preventive measures: technically control the noise source by dampening machinery and pump. Control noise propagation by establishing soundproof rooms. Individuals should wear earplugs or earmuffs and conduct health monitoring. 3. High temperature. Source: heat released during production and inadequate heat dissipation, such as temperatures exceeding 40 degrees Celsius in hot oil rooms or frosting rooms, or high temperatures during summer. Hazards: it can cause disturbances in water and salt metabolism, affect various bodily systems and in severe cases lead to heat stroke or even be life-threatening. Preventive measures. Technically, design processes reasonably, evacuate and isolate heat sources, and enhance ventilation and cooling. Individuals should wear heat-insulating clothing at strengthen organizational management and arrange work schedules reasonably and conduct health monitoring. 4. Industrial toxins. Toxins refer to substances that once accumulated in the body to a certain level, cause biochemical or biophysical changes in tissues that interfere with or disrupt normal physiological functions, result in temporary or permanent pathological conditions, and may even be life-threatening. Industrial toxins. Toxins encountered during industrial production. Industrial toxins can be classified according to their chemical nature, the properties of their toxic effects, and the organs or systems they damage. Source: raw materials, auxiliary materials, intermediates, etc. Used or produced during the production process. The phosgene and liquid ammonia that Jiaoli is exposed to are examples of industrial toxins. Hazards. They can cause acute poisoning, chronic poisoning, or subacute poisoning, damaging multiple organs and systems in the body. Preventive measures. Technically, adopt methods such as substitution, process modification, and isolation. Individuals should wear gas masks, etc., and in management, ensure proper chemical registration and safety education. 5. Radiation. It is the phenomenon in which a portion of the electromagnetic energy emitted from a source separates from the source and propagates outward without returning, with the energy diffusing in the form of electromagnetic waves or particles, such as alpha particles, beta particles, etc. Source: natural radiation and man-made radiation, as seen in chemical production, where devices such as radiation level gauges are used. Hazard: ionizing radiation can induce cancer and affect the reproductive system, among other adverse effects. Preventive measures. Technically, use shielding methods and remote control measures. Individuals should wear anti-radiation clothing, etc., and conduct health monitoring. Let's return to Jiaoli's case. Analyze the sources of the occupational disease hazard factors in this case, the potential dangers they may cause, and the necessary preventive measures. Dust. Its source is the handling and storage of materials in the finished product storage area of the polycarbonate plant and the bisphenol A raw material area, which may cause pneumocomiosis, affect the air environment, and lead to dust explosions. Preventive measures include using enclosed transportation, individuals wearing dust masks, and regular medical examinations. Noise. Its source is the operation of machinery in the ammonia compressor area and the distillation section fan area, which may cause hearing damage and harm to extra auditory systems. Preventive measures include dampening equipment, establishing soundproof rooms, and individuals wearing earplugs, etc. High temperature. Its source is the heat released during production in the hot oil room and the phosgene room, which may cause disturbances in water and submetabolism and harm to bodily systems. Preventive measures include isolating heat sources, enhancing ventilation and cooling. Individuals wearing heat insulating clothing, and arranging work schedules reasonably. Industrial toxins. These arise from raw materials or processes involving substances such as naphthalene, bisphenol A, sodium hydroxide, liquid ammonia, carbon monoxide, chlorine, and phosgene, and may cause acute poisoning, chronic poisoning, or subacute poisoning. Preventive measures include process modification, toxin, individuals wearing gas masks, and strengthening chemical management. Through this case, everyone should have a clearer understanding of the knowledge learned earlier. Right? Class summary. Today we have learned the definitions and classifications of occupational disease hazard factors with a focus on understanding the common occupational hazard in the chemical industry, including the sources, dangers, and preventive measures for dust, noise, high temperatures, industrial toxins, and sources of radiation, hazards, and protective measures. This knowledge is crucial for our future work in the chemical industry, and I hope everyone will review and consolidate it after class and pay more attention to potential occupational hazards around them.